All right, so now we can talk about dot product of two vectors. This theory kind of jumps us into the very tip of kind of more stuff you're going to be doing in the next course, Calculus 3 and everything. But um, we need to get us a good basis here. So we've studied two operations with vectors. We got vector addition and multiplication by a scalar, each of which is going to yield us another vector. So in this section, we're going to study a third vector operation called the dot product. This product yields a scalar rather than a vector. So to describe the dot product of u, we let u equal u1, u2, so it's two elements, and v equals v1, v2, which is also two elements. In order for us to do a dot product, we must have the same number of elements in each of our vectors. They both must have two, or they both must have three. So if we're going to do one that has two elements, the dot product u dot v, defined like this, that doesn't mean multiplication, it means dot product, would be equal to the first components multiplied together of each of our vectors, and then the second components multiplied together, and then we're going to add them together. So it's going to be u1 v1 plus u2 v2 would be our multiplication and additions there. If we had vectors that were three-dimensional, so u equals u1, u2, u3, and v equals v1, v2, v3, then the dot product u dot v would be u1, v1 plus u2, v2 plus u3, v3. In terms of dot product, it really doesn't get very much more complicated than that. We can find angles between them using alternate methods, but all in all, it's pretty straightforward and easy. Now we do got some properties. So if we let u, v, and w be vectors in the plane or in space, and we let c be a scalar, then u dot v is equal to v dot u. So our commutative property, doesn't matter which one comes first, they're still going to be equal. Next, we could have as our distributive property, u dot the quantity v plus w would be u dot v plus u dot w. We can have a scalar multiple times the dot product, c times the dot product of u dot v, would be cu dot v or u dot cv. It does not matter which one we carry that scalar to, but we'll only carry it to one since the dot product will just give us a number. 0 dot v, where 0 is actually the zero vector, is just 0. V dot v is equal to the magnitude of v squared. So we just got to kind of think about how we see different things and everything. So besides doing the dot product, we can also use this in order to figure out the angle between the two vectors. So the angle between two non-zero vectors is the angle theta, where theta is greater than or equal to 0 and less than or equal to pi. So we don't have any that are greater than pi. It has to be inside of the first and second quadrant. This will be between their respective standard position vectors, as shown below. So the next theorem we're going to learn on the next page is going to show us how to find this angle using the dot product. Notice that our angle theta is here. We created this triangle by using the piece v minus u as it's written here. So when the angle between two vectors is known, if we rewrite a theorem in the form of u dot v is equal to the magnitude of u times the magnitude of v times cosine of theta. So this is going to produce an alternative way to calculate the dot product, and it will also give us a way to figure out the angle between them by rearranging terms. Because if we know v, we know u, we can find their magnitudes, we can find the dot product, and then we can find our angle theta. So note that in this theorem that because the magnitude of u and magnitude of v are always positive, u dot v and cosine of theta will always have the same sign. So we have some possible orientations of our two vectors here. In the first case, if they are in opposite directions, so v is going to the right, u is going to the left, then theta in between them is equal to pi, and the cosine of theta would be equal to -1. So it's going to be important to understand what this cosine of theta in each one of these cases gives us, because it's going to help determine what we're looking at. If you know the picture of what they are, then we can kind of guess and see where we need to be. If our dot product is less than 0, then we have that theta is between pi over 2 and pi. And cosine of theta is less than 0 and greater than -1. If our dot product is 0, so in other words, this case right here, this is an important case. If we know that the dot product is 0, that means that theta is equal to pi over 2. And it also means that they are orthogonal. Orthogonality gives us a lot of traits and everything, so it's good to know if our two vectors are orthogonal or not. If u dot v is greater than 0, theta would be greater than 0 and less than pi over 2. Cosine of theta is greater than 0 and less than 1 in this case. If our two vectors are going in the same direction, then that means that theta is going to equal 0 and cosine of theta is equal to 1. So we have to be able to pay attention and kind of understand our orientation of what are we looking at if we're given a picture. If we drew it out, what would we be looking at, because that would kind of help us figure out some different items. So from that theorem, 11.5, we can see that two non-zero vectors meet at right angle if and only if their dot product is 0. Two such vectors are said to be orthogonal. So the vectors u and v are orthogonal when our dot product is 0. So sometimes the question is just going to ask us, are these two vectors orthogonal? Well, we just simply do the dot product to see what value we get. The only way they're orthogonal is if the dot product is 0. So now let's actually look at that. So it says find the dot product of v dot w and the angle theta for v equals 4i plus 7j and w equals -6i minus 5j. Well, first thing, let's find v dot w. So 4 times -6 plus 7 times -5, -24 minus 35, -59. Well, that told us the dot product. So right now we know they're not orthogonal because of the fact that we did not get 0 there. So we found our dot product v dot w. Well, now we need to find theta. So we know that v dot w is equal to the magnitude of v times the magnitude of w times cosine theta. Well, we know the v dot w, so we got -59. The magnitude of v is 4 squared plus 7 squared and the square root of it. So 16 plus 49 is the square root of 65. The magnitude of w is the square root of -6 squared plus -5 squared, which is the square root of 61. So square root 61, square root 65, cosine theta. So that means theta is equal to inverse cosine of -59 divided by square root 61, square root 65. So that would tell us that theta is approximately 2.78468 if we went to 5 decimal places. So if we scan back to our previous slide right here, so we had that our dot product was less than 0. So we know that theta is between pi over 2 and pi, and therefore that matches what we just found here, because this is less than 3.14 but greater than pi over 2, which is approximately 1.6 something. So we're pretty good right there. So now we're told, find the angle theta between the following vectors, v equals negative 8i minus 4j minus 5k, and w equals negative 5i minus 5j plus 12k. So the first thing we need to find is v dot w. So v dot w is negative 8 times negative 5 plus negative 4 times negative 5 plus negative 5 times 12. 40 plus 20 minus 60 gives us 0. So since our dot product is 0, that means they're orthogonal. Since they are orthogonal, that means that theta is equal to pi over 2. So those are our two conditions that we were looking for there. Now, that was kind of our little first jump into 3D in terms of a three-dimensional vector that has I, J, and K as components. So the next thing we want to kind of talk about is directional cosines. So in space, it is convenient to measure direction in terms of the angles between the non-zero vector v and the three unit vectors I, J, and K, as shown below. So since, if you notice that we've got gamma comes off the K, beta comes off of the J, and alpha comes off of the I. So we got three different letters, which they're all just denoting a different angle. So no worry, we just have to kind of keep that in mind whenever we're finding these. So the angles alpha, beta, and gamma are the direction angles of V, and cosine alpha, cosine beta, and cosine gamma are the direction cosines of V. So because V dot I is equal to the magnitude of V times magnitude of I times cosine alpha, which is, we'll simplify to magnitude of V times cosine of alpha, because I is our standard unit vector, so it has a magnitude of 1 always. And we know this because V dot I is V1, V2, V3 times 1 are dotted with 1, 0, 0, which is just V1. So it follows that cosine of alpha is equal to V1 divided by the magnitude of V. That would be our directional cosine for alpha. In a very similar format, we could find the other two for cosine beta and cosine gamma. So just understand cosine of alpha is V1 divided by magnitude of V. Cosine beta is V2 divided by magnitude of V. And cosine gamma is equal to V3 divided by magnitude of V. We must note that alpha is the angle between V and I. Beta is the angle between V and J, and gamma is the angle between V and K. So we're told, find the magnitude of our magnitude and directional cosines of the vector V equals negative 8i plus 6j plus 7k. Then we want to write V in terms of its magnitude and its directional cosines. So first thing we want to find is the magnitude of V. So that is the square root of negative 8 squared plus 6 squared plus 7 squared. So that is the square root of 64 plus 36 plus 49 which is the square root of 149. So we're told find the direction cosines. So therefore, we have cosine alpha, cosine beta, and cosine gamma. So cosine of alpha is going to be -8 over square root 149. Cosine of beta is 6 over the square root of 149. And cosine of gamma is 7 over the square root of 149. Now, if we were to write this in terms, so we found our directional cosines, we found the magnitude. Now we need to write v in terms of its magnitude and directional cosines. So that means v equals the square root of 149 times -8 over square root 149 times I plus 6 over the square root of 149 times j plus 7 over the square root of 149 times k. So that would be our two pieces that we would have to find in terms of this problem right here. So consequently, for our directional cosines, any non-zero vector v in space has the normalized form of v divided by magnitude of v is equal to v1 over magnitude of v times I plus v2 over magnitude of v times j plus v3 over magnitude of v times k, which is simply cosine alpha I plus cosine beta j plus cosine gamma k. And because v divided by magnitude of v is a unit vector, then it follows that cosine squared alpha plus cosine squared beta plus cosine squared gamma is equal to 1. This can be helpful in finding what we need to find depending on what our questions are asking and applications we can see. So now we can take what we've been learning about magnitudes, direction angles, dot products, and we can kind of move it to some more application pieces. So the first thing that we're going to talk about are projections. So if u and v are non-zero vectors, when the projection of u onto v is given, projection of u onto v is equal to u dot v divided by the magnitude squared of v all times v. So the projection of u onto v can be written as a scalar multiple of a unit vector because v divided by magnitude of v right here, this is just 1. So this is just our k value because this is equal to 1. So k times v over v gives us k is equal to u dot v over magnitude of v. V over magnitude of v is 1. So this is just the magnitude of u times cosine of theta. So the next thing we can talk about is how can we take this and use work as an example. Work is a very common application of dot products in terms of physics and everything. So most likely you're going to see this inside your physics classes as well. So the work done by the constant force F acting along the line of an object is given by work equals magnitude of force times distance. So the magnitude of F times the magnitude of the vector PQ. So as shown, so what we're talking about is that if we take this box at this point P and we move it with a force F over here to get us to Q, we're using this much work to get it there. Think about you're trying to move a sofa, you're trying to move a refrigerator. There's a certain amount of work that you're going to have to do in order for it to actually begin to move and everything. So that's kind of what we're kind of thinking about. And what we're doing is we're trying to move it along in this case, a flat line. So when the constant force F is not directed along the line of motion, you can see that the work W done by the force is given by a slightly different thing using projections. So work is equal to the magnitude of the projection of F on the PQ times the magnitude of the vector PQ. So if we rewrite that projection piece, we're going to get cosine theta times the magnitude of F times the magnitude of PQ, or in other words, F dot PQ. So this is if we're acting at an angle instead of straight on. If we're pushing this straight on, we have different formulas than if we push at an angle. So this notion of work is summarized in this definition. So the work W done by a constant force F at its point of application moves along the vector PQ is one of the following. W equals the magnitude of the projection of F on the PQ times the magnitude of PQ. This is projection form. If we think about this in dot product form, then it's W equals F dotted with the vector PQ. You might have also seen formulas before that's work is equal to FD cosine theta. Same exact theory right there. So let's look at this example right here. So we're out on the farm. We want to close a sliding door. A person pulls a rope with a constant force of 50 pounds at a constant angle of 60 degrees. As shown in this figure. We want to find the work done in moving the door 12 feet to its closest position. So let's zoom in a little bit on this picture. So notice we got our point P and we're pulling this rope. So the person here is pulling this rope and we're going to go 12 feet as stated right here. So we've got this that we got to work out. So we can use the exact formulas we were just working with. So the solution to this, so using a projection, we can calculate the work as the following. The magnitude of the projection of F on the PQ times the magnitude of PQ. So if we rewrite the projection as cosine 60 degrees times the magnitude of the force times the magnitude of PQ. So cosine of 60 degrees, because if we go back right here and look at our picture now, we're pulling at a constant of 50 pounds at an angle of 60 degrees for 12 feet. So cosine of 60 is 1/2. The magnitude of our force is 50. Magnitude of PQ, our distance is 12. So it's FD cosine theta is really what we're doing here. In order to figure this out. So when we do that, we get 6 times 50, which is 300 foot-pounds as our answer here.